Welcome to AI Paper Podcasts. Today we're cracking open the technical report for Seedream 3.0.
Right, this is ByteDance's new bilingual image generation model.
Exactly, and it's making waves, currently sitting at the top of the artificial analysis arena leaderboard. I mean, it's even outperforming huge names like GPT-4o and Imagen 3.
Yeah, it's pretty impressive.
So the big question for us, for the technical folks listening, is how? How do they actually pull this off?
That's the million-dollar question. Seedream 2.0, it was good, definitely a strong model.
Sure.
But it wasn't perfect. It had some limitations, especially with really complex prompts. Getting fine-grained typography right was tricky too.
Right, the text rendering.
Especially text rendering. And, hitting that top-tier aesthetic quality consistently, plus pushing past certain resolution limits.
Okay.
So what's really fascinating about Seedream 3.0, I think, is how systematically they seem to have addressed these issues.
So we're going to dive deep.
Yep. We'll dissect the key technical innovations, looking at the whole pipeline, everything from the data they used, the training methods, right through to deployment.
The goal being to really understand the engineering behind this performance leap.
Exactly. What makes it tick?
So our mission today is to pull out those crucial technical insights. What are the clever architectural choices, the new training tricks, the data handling, stuff our audience, AI researchers, ML engineers, can actually learn from.
Right. And for anyone needing the quick version, maybe for that first minute edit.
Yes, the short form summary.
Okay, here's the essence. Seedream 3.0 is a major step up. They've really focused on smarter data use with things like Defect-Aware training and dual-axis sampling.
Defect-Aware, okay.
Yeah. Then in pre-training, they've got mixed resolution training and this thing called Cross-Modality, RoPE, for better understanding between text and image.
RoPE across modalities. Interesting.
Post-training uses aesthetic captions and a pretty powerful VLM-based reward system. And finally, for speed, they've got consistent noise expectation and importance-aware time-step sampling.
Wow. Okay, so what's the result of all that?
The upshot is basically a model that's better at matching texture prompts, nails text rendering, especially Chinese characters, looks aesthetically better, and can natively output 2K resolution images. Oh, and with faster inference.
Faster too. Nice.
Yeah, it's really a whole package of improvements. They didn't just tweak one thing.
All right. Sounds comprehensive. Let's get into the nitty-gritty then, starting where it all begins. The data. You mentioned Seedream 2.0 was quite strict with its data.
They were maybe a bit too strict in hindsight. Their filtering process apparently threw out about 35% of their potential training data.
35%. Why?
Mostly due to what they called minor artifacts. Things like small watermarks, maybe some overlaid text, stuff that wasn't perfect.
But potentially still useful data. You're losing a lot of signal there.
Exactly. That's a huge chunk to just discard.
So Seedream 3.0 takes a different, maybe more efficient approach.
They do. They call it a defect-aware training paradigm.
Okay, what does that mean in practice?
Well, the key part is a specialized defect detector. They trained this thing on about 15,000 annotated samples using active learning, so it got really good at spotting different kinds of visual defects and drawing bounding boxes around them.
So it knows where the problems are, not just if there's a problem.
Precisely. So now, instead of just tossing the image, if the defects cover less than 20% of the area, that seems to be their magic number.
They probably tuned that threshold.
I'd assume so. If it's under 20%, they keep the sample, but, and this is the clever bit, they use mask latent space optimization.
Okay.
Basically, when they're calculating the diffusion loss during training, they use a spatial attention mask. This mask tells the model to effectively ignore the gradients coming from those defect areas.
So it's like saying, pay attention to the good parts, ignore this little watermark over here.
Exactly that. Learn from the clean parts of the image.
That's smart. A way to salvage data that's mostly good. What was the impact? Did they get more training data overall?
They did. It led to a 21.7% increase in their effective training data. And crucially, they managed this without destabilizing the training process.
So more data, same stability, that's a win.
Definitely. It shows you can be smarter about handling imperfect data instead of just throwing it away. Much more efficient.
Absolutely. Okay, the report also mentions a dual-axis collaborative data sampling framework. Sounds fancy. What's the core idea there?
It's about balancing the data they sample along two different lines, or axes.
Axis being?
One axis is visual. They use hierarchical clustering, same as in 2.0 actually, to make sure they get a good mix of different visual patterns and styles. So it's not just all landscapes or all portraits.
Okay, balanced visuals. And the second axis?
That focuses on the text, the semantic level. Here they brought in TF-IDF term, frequency inverse document frequency.
TF-IDF, to balance the descriptions.
Exactly. You often get this long-tail distribution in text descriptions, right? Some words or concepts are super common, others are rare. TF-IDF helps balance that out, making sure the model sees a more representative spread of textual concepts, not just the most frequent ones.
Makes sense. You don't want it only learning about dogs and cats.
Precisely. And then there's the Cross-Modal Retrieval System. This sounds like it's about tightening the link between the images and their text descriptions.
How does that work?
They built this joint embedding space where images and text pairs live together. Apparently, it's state-of-the-art on some benchmarks. But the cool part is it's dynamic. It actively optimizes the data set.
Dynamically? How?
A few ways. First, they can use it to inject specific knowledge. Like if they want the model to get better at generating, say, Art Deco architecture, they can retrieve more relevant image-text pairs for that concept.
Targeted improvement. Nice.
Second, it helps calibrate the data distribution using similarity-weighted sampling. So maybe higher quality or more representative pairs get sampled more often. And third, it uses neighboring pairs in that embedding space. So an image-text pair can kind of learn from other nearby semantically similar pairs, strengthening that cross-modal connection.
So it's a much more active, curated approach to building the data set.
Yeah, much more interactive than just scraping and filtering.
Okay, really interesting data strategies. Let's shift to the model pre-training. They said the core architecture, MMDIT, is the same as Seedream 2.0, just bigger.
Fundamentally, yes. MMDIT is good for handling both image and text tokens together. They did increase the total parameter count, which usually gives the model more capacity.
But the real innovations are elsewhere.
Yeah, I think the specific techniques they added are more impactful, like this mixed resolution training.
Right. What's the benefit there?
Well, transformers are naturally pretty flexible with input sizes. Seedream 3.0 really leans into that. They train it on batches containing images of all sorts of aspect ratios and resolutions mixed together.
All at once.
Yeah. They start pre-training at a lower average resolution, maybe around 256 squared. Then they fine-tune progressively on higher resolutions, going from 512 squared all the way up to 2048 squared.
Wow, 2K native training.
And to make sure the model knows what resolution it's aiming for, they feed it a size embedding as an extra piece of information, like a condition.
So showing it lots of different sizes makes it better at handling any size you ask for later.
Exactly. It massively increases the diversity of the training data and, critically, helps it generalize much better to resolutions it hasn't explicitly seen during training. It's more robust at inference time.
Makes sense. Then there's cross-modality ROP. I know rotary positional embeddings, but cross-modality, how does that work?
So in Seedream 2.0, they had something called scaling ROP, which helped with different aspect ratios. For 3.0, they extended this idea specifically to improve how well the visual parts and the text parts of the input understand each other. They basically treat the text tokens, the sequence of words, as if they were a 2D structure, like a single row of pixels 1L. Then they apply 2D rope E to these text tokens.
So text gets positional information like an image badge.
Sort of. The key is that the column-wise position IDs for the text tokens are set up to be consecutive, following right after the image token positions. It creates a kind of shared positional map for both the image and the text.
A unified spatial understanding across modality.
Exactly. It helps the model better understand relationships within the image and within the text, intramodality, but more importantly, the relationships between the image and the text, cross-modality.
Which should directly help with things like following complex instructions or rendering text accurately in the image.
Precisely. Better alignment, better text rendering.
Got it. And training objectives. They mentioned flow matching.
Yes, flow matching is gaining traction, seems to work well for diffusion models, but they also added something else. Representation alignment loss, or REPA.
REPA, what's that aligning?
It calculates the cosine distance between the features produced inside their MMDIT model at intermediate layers and the features extracted from a powerful pre-trained vision model, Dino 2L.
So, trying to make its internal understanding similar to another strong vision model.
Kind of like giving it a guide. They found that adding this RPA loss with a specific weight, Google 0.5, actually sped up the convergence of their main text-to-image training quite a bit.
Faster convergence is always good. Saves compute.
Always a bonus. And the last pre-training bit was resolution-aware time-step sampling. sounds linked to the mixed resolution training.
How so?
Well, in diffusion, you sample time steps, which correspond to noise levels. Seedream 3.0 makes this sampling process adaptive. It depends on the data, especially the resolution.
So it samples noise differently for low-res versus high-res images.
Essentially, yes. They shape the probability distribution for picking time steps. It starts with a logit normal distribution, but then they shift it based on the training resolution.
Why shift it?
Generally, for higher resolution images, they shift it towards sampling lower signal-to-noise ratios, meaning less noise, more signal.
Because higher-res images have finer details.
Exactly. Those finer details are often learned better when there's less noise obscuring them. Then, at inference time, when you ask for an image, they calculate another shift factor based on the resolution and aspect ratio you want. So the whole denoising path is tailored to the output characteristics.
Very adaptive. Okay, that covers pre-training. Let's talk post-training refinements. The pipeline looks similar to 2.0 CT, SFT, RLHF, PE, but with a key difference.
Right, the overall flow is familiar. Continuing training, supervised fine-tuning, reinforcement learning from human feedback, and prompt engineering. But interestingly, they dropped the explicit refiner stage.
No separate upscaler. Why?
They attribute it to Seedream 3.0 just being better natively. It can directly generate high-resolution images up to that 2048 squared range we mentioned. So the thinking is, you don't need a separate model just for upscaling anymore.
That's a testament to the core model's improvement. They also mentioned using aesthetic captions during SFT. What are those?
Yeah, this is interesting. They trained separate captioning models specifically to describe the images used in their CT and SFT datasets.
But not just basic captions.
No, these go further. They include details about aesthetics, the artistic style, even the layout and composition. Think golden hour lighting, Dutch angle, minimalist composition.
So explicitly teaching the model the language of aesthetics and style.
Exactly. It gives the model a richer signal about what makes an image visually appealing or stylistically specific. This helps it respond better to prompts asking for certain looks, and generally improves control after prompt engineering.
Makes sense. Train it on the concepts you want it to understand. And there's also a resolution balancing strategy in post-training.
Yes, this ties back to the mixed resolution idea. During post-training, they make sure they're sampling images across the full range of resolutions adequately.
Why is that important, specifically in post-training?
It ensures the model doesn't just get good at generating, say, 124 by 124 images, but that it maintains strong prompt following and quality across different scenarios, whether you ask for a wide banner or a square portrait. Better versatility.
Got it. Now, reward models for RLHF, they moved away from the CLIP, which Seedream 2.0 used.
Correct. Seedream 3.0 uses vision language models, VLMs, as the reward framework.
Why the switch to VLMs?
They argue VLMs have stronger foundational capabilities, a deeper understanding of both vision and language, and importantly, better potential for scaling the reward signal.
Okay, so how do they get a reward signal from a VLM? It's not inherently a reward model.
Right. They use a technique inspired by LLM reward modeling. They basically frame the prompt and the generated image as a query to the VLM, asking something like, does this image accurately and aesthetically represent the prompt?
Like asking the VLM a yes-no question.
Essentially. They then derive the reward score from the normalized probability the VLM assigns to the yes token, or a similar affirmative response. It's like tapping into the VLM's judgment.
Clever. Using the VLM's world knowledge as a judge, and they scaled this VLM judge up.
Significantly. They went from a 1 billion parameter VLM reward model up to over 20 billion parameters.
Cool.
And they found clear evidence of reward model scaling. Bigger reward model led to better alignment with human preferences in the final generated images. Size matters for the judge, apparently.
Fascinating. Okay, powerful model, but how do they make it fast? Let's talk acceleration.
All right, performance is key. Their framework builds on some known techniques like HyperSD and Rayflow, but adds new twists.
Such as?
One core idea is rethinking the diffusion trajectory. Usually, all samples sort of aim for the same standard Gaussian noise distribution at the end of the forward process.
Right, the prior.
Here, they allow each sample to follow its own adaptive generative trajectory. The idea is to reduce path collisions in the latent space.
Path collisions, meaning different images ending up too close together in the noise space.
Kind of. By giving each sample a more unique path back from noise, they aim for less overlap, which they believe improves both the stability of generation and the diversity of the outputs.
More individualized generation paths. Interesting concept. What about consistent noise expectation? How does that speed things up?
This is about making the denoising steps smoother. They introduce a unified noise expectation vector. Think of it as a reference point. It's estimated from a pre-trained model and provides a consistent target for the noise prediction across all the different time steps in the sampling process.
A global reference for noise.
Yeah. By keeping this expectation consistent, the model doesn't have to drastically reevaluate the noise structure at every single step.
Yeah.
This consistency allows them to compress the number of sampling steps needed during inference.
Fewer steps means faster generation.
Exactly. They argue this maximizes the probability coherence between the forward, adding noise, and backward removing noise paths, leading to stable sampling and good reconstruction with fewer NFE's noise function evaluations.
Fewer steps, same quality, the holy grail. And learning to sample important time steps, what's that about?
So, standard diffusion training often samples time steps uniformly, just picks random noise levels. But the problem is, not all noise levels are equally informative for learning.
Some steps teach the model more than others.
Right. Some steps might contribute much more to reducing the training loss. Uniform sampling can be inefficient, spending time on less critical steps.
So they want to focus the training effort.
Precisely. They use importance sampling. They employ a technique called stochastic Stein discrepancy, plus a small neural network. This network learns to predict which time steps are likely to be most important for reducing the loss for a given data point.
So it learns a smarter way to pick time steps during training.
Yep, a data-dependent distribution over time steps. Focus the compute where it matters most. This leads to faster convergence in training.
Smarter training, leading to potentially better models and faster inference. And the result of all this acceleration work.
They claim their efficient few-step sampling achieves results that are as good as, or even better than, baseline models needing 50 or more steps, NFEs.
Wow, that's a big reduction.
Yeah, across aesthetics, text-image alignment, structure, it shows their trajectory design and consistency methods are really paying off. For other things like quantization, they said they mostly followed their Seedream 2.0 approach.
Okay, we've covered the tech. Now the proof is in the pudding. How does it actually perform? That leaderboard ranking is pretty striking.
It is. #1 overall on the artificial analysis leaderboard, ahead of GPT-4o, Imagen 3, Midjourney. That's significant.
But not just overall, but in subcategories too.
Yeah, they report leading in most style categories, photorealistic, anime, art, and subject categories like portraits, fantasy, futuristic.
Impressive claim. But leaderboards can be, specific benchmarks. What about their own internal, more detailed testing?
Good point. They did conduct extensive human evaluations using a benchmark set, Convench 377. It has diverse prompts covering cinematic, art, design, practical uses.
And how did Seedream 3.0 fare there?
It significantly beats Seedream 2.0 and other top models on text-image alignment, how well it matches the prompt and structural fidelity, getting objects and scenes right.
What about aesthetics? Midjourney is often seen as the king there.
Interestingly, Seedream 3.0 scored higher overall aesthetically than Midjourney in their tests, although drilling down, Midjourney was still slightly better in the pure art category, while Seedream 3.0 was stronger in design.
A more balanced profile, perhaps.
Seems like it. Imagen 3 did well on alignment structure, but lagged on aesthetics. Midjourney, great aesthetics, but weaker on following instructions precisely, or structure. Seedream 3.0 seems to hit a better sweet spot across the board according to their evil.
Okay, human evil sound positive. What about automatic metrics?
Consistent story there. They used benchmarks like Evil Muse for alignment and HPSV2, MPS, plus internal metrics for image quality. Seedream 3.0 came out on top across all of them.
Any specifics on Evil Muse?
Yeah, significant gains over 2.0 in understanding objects, activities, locations, even things like food and spatial relationships. And they highlighted hitting over 0.3 on HPSV2 for the first time, which supposedly indicates very good alignment with human aesthetic preferences.
And they provide examples to back this up.
Yes, lots of figures in the paper. They show how the improved alignment helps capture subtle things like micro-expressions in portraits or understand complex descriptions like generating a 3-view drawing. They also show better structural stability, like rendering limbs correctly in motion, and just overall better quality in color, lighting, and texture.
Okay, solid performance claims. Now, text rendering. Seedream 2.0 was already known for being good at this, especially Chinese text. Did 3.0 improve further?
They definitely focused on it. They used a benchmark with 180 Chinese and 180 English prompts, logos, posters, handwriting, etc., and measured things like availability rate, is the text generally okay and the image looks good, and character level accuracy.
And the results?
Superior performance again. They hit a 94% availability rate for both Chinese and English text. That's a big jump. 16% better for Chinese compared to Seedream 2.0.
94% availability is very high.
It is. And the fact that their availability rate and character hit rate were almost the same suggests it's not making many errors in terms of layout or how the text integrates with the image medium.
So their native rendering approach works. No need for separate text plugins.
That's what they argue, yes. These results seem to validate embedding the text generation directly into the diffusion process.
What about really dense text, like paragraphs of small print? That's usually very hard.
Historically, yes. But they show examples where Seedream 3.0 handles this surprisingly well. Good precision on small characters, natural layout. They even compared it to GPT-4o on dense text.
How did that comparison go?
Seedream 3.0 apparently handled dense Chinese text better, especially typesetting and aesthetics. GPT-4o was reportedly better with small English characters and some specific things like latex symbols, so different strengths maybe.
Interesting. Another area they tackled is photorealistic portraits, addressing that AI look.
Right, that overly smooth, sometimes oily skin texture people complain about.
How did they evaluate improvement here?
They used an Elo Rating System with human evaluators. People saw two portraits side by side and picked the one they felt was more realistic and conveyed emotion better. They compared Seedream 3.0 against 2.0, Midjourney V6.1, FLUX Pro, Ideogram.
And the winner was?
Seedream 3.0 and Midjourney V6.1 tied for first place, significantly ahead of the others.
So Midjourney is still strong on portraits too?
It seems so. The examples show Seedream 3.0 getting realistic skin textures, wrinkles, facial hair, scars much better, avoiding that artificial look. Though they note Midjourney might still have a slight edge in conveying emotional expression.
A subtle difference.
But Seedream 3.0 has another trick. It can generate these portraits directly at higher resolutions, like 2048 by 2048. They show examples where this further enhances the texture detail, pushing it towards professional photo quality.
Native high-res portraits, that's a plus. Okay, lastly, they compared Seedream 3.0 with GPT-4o more broadly. Tricky comparison since GPT-4o's image generation API isn't widely available for benchmark testing.
Exactly. So they focused on specific use cases like image editing.
How do they compare there?
GPT-4o can edit based on prompts, but apparently sometimes struggles to keep the original image elements consistent things, like preserving the person's identity, ID consistency, or the overall style.
In Seedream.
They used C-Edit, which is based on Seedream tech. It reportedly did better at preserving the original image ID while still following the edit prompt. Another model, Gemini 2.0, kept original pixels well but had issues with color naturalness. C-Edit seemed like a good balance for typical edits.
What about editing text within an image?
Seed-Edit, leveraging Seedream 3.0's text skills, could apparently detect, delete, or change text accurately and integrate new text smoothly. GPT-4o could do the text editing task itself, but again, sometimes failed to preserve the surrounding original image well.
Preservation seems key. And just overall generation quality, head-to-head.
Based on the examples they showed, Seedream models generally had better color, texture, clarity, and aesthetics. They mentioned GPT-4o images sometimes having a kind of dark yellowish hue and noticeable noise.
So the takeaway is, GPT-4o is incredibly versatile, multimodally, but for pure, high-fidelity image generation and editing, especially preserving details in text, Seedream 3.0 seems to have an edge currently.
That seems to be the conclusion from their report, yes. It highlights that different models might excel in different areas. Seedream 3.0 is clearly a major step forward, specifically in bilingual, high-quality image generation.
The systematic improvements across the whole stack, data, training, acceleration really paid off.
Definitely. The sum is greater than the parts here.
And for our technical audience, there are some really valuable takeaways here, right? The defect-aware training, the cross-modality rope E, consistent noise expectation. These are concrete techniques people might explore.
Absolutely. These offer genuine insights into pushing diffusion models further, better quality, more efficiency, finer control. These are tools others can potentially adapt or build upon.
And it sounds like they're not stopping. The paper hints at future work.
Yeah, they mention wanting to improve emotional expression even more in portraits and tackling more complex editing tasks, so expect more evolution in this space. The comparison with GPT-4o also just shows how dynamic the whole multimodal AI landscape is right now.
Okay, so let's leave our listeners with a final thought. Given that Seedream 3.0 can generate native high-resolution images and do it pretty efficiently, how do you think this might change things? Could it accelerate how high-quality customized visuals get integrated into real-time apps or into the daily workflows for technical pros like yourselves?
That's a good question. Real-time high-res generation.
Definitely something to think about. The potential impact on creative workflows, maybe even scientific visualization or engineering design, is quite significant.